Welcome to section 2.2, day 2, polynomial functions. We're doing zeros and turning points today. So we want to determine the number of zeros of a polynomial function without graphing it. We want to determine the number of turning points without graphing. We want to write higher degree polynomials in quadratic form. And we're also going to be graphing using our turning points and our zeros. So our key concept, zeros and turning points of polynomial functions. A polynomial function f of degree n greater than or equal to 1 has at most n distinct real zeros and at most n minus 1 turning points. So you take your power, whatever your power is, like the one shown here, we have 3x to the 6th. That means there are 6 possible real zeros. And we do the 6 minus 1, there are 5 possible turning points. There will be at most 5 turning points. When you look at the graph, you'll see it has 3 real zeros looking at it and 3 turning points. When we do these turning points in in zeros, we're looking for the potential of what they have, and we'll do some solving to see what we actually really do have. So here we're just given a function that says state the number of possible real zeros and turning points of the function. And then we want to determine the real zeros we actually have by factoring. So first, just looking at it, we have a power of 3. Also, again, make sure you're always in standard form. Power of 3, which means we have 3 possible zeros. And we have 3 minus 1 turning points. That means we have 2. I'm just going to use abbreviation today. We have 2 turning points. And now we're going to factor it to see what we actually have for zeros. So I'm going to set f of x equal to 0. I'm going to factor out an x. And then we have x squared plus 5x plus 4. And then we factor it. And we get x plus 4, x plus 1. When it says to do this, make sure you're showing your factoring. We are going to set all the factors that have a variable in them equal to 0. When you solve them all, you'll get that x is 0, negative 4, and negative 1. This one does have 3 real zeros. If we graph it, we would see where it crosses, and we'd have 2 turning points. And from what we did yesterday, we should know what this starts at and where it ends, since it's a cube function, how it starts and how it ends. All right, for the second one, we have a power of 4. So we have 4 possible zeros. And we also, like I said, we have a power of 4, so we have 3 potential turning points. At most, we have 3 of them. We can factor this. We have x to the 4th in the first term and x squared in the middle term and a constant in the end. This is sort of the same as having x squared minus x plus a number. The way we get back to x to the 4th is if we have x squared times x squared. How do we get from 36 to negative 13? What multiplies the 36 that adds to that? A negative 4 and a negative 9. We're finding 0, so set f of x equals 0. This can be factored further because it's a difference of squares. This is x minus 2, x plus 2. And x squared minus 9 is also a difference of squares. X minus 3, x plus 3. And then we get our zeros at x equals 2, negative 2, 3, negative 3. We have 4 real zeros. This is a power of 4. This will somewhat resemble for n behavior, it would resemble the quadratic function. And since we do have 4 zeros, we would have 3 turning points. We'll see that as we go through. All right, so quadratic form. The last one we did not have in quadratic form per se, but we had it in a form we could factor. For some of you, it might be easier to put it in what we call a quadratic form. So what we can do is we can change that previous equation into where it's squared term for your first one. So if we have something that's written as au squared plus bu plus c, where a does not equal 0, otherwise you don't have a squared term in the front, and u is just some expression of x. So if we have x to the 4th minus 5x squared minus 14, we can change our x squareds into something else. And what we're going to do is we're going to give it another variable name. We're going to say u, in this case, is x squared. And when we rewrite it, we can rewrite it like this as u squared minus 5u minus 14. And this is sometimes easier visually to see how to factor u squared instead of x to the fourth. This is called quadratic form. And for some of you, it'll be easier to factor when it's in this form. After we'd factor it, then we'd have to plug the x squared back in for you to solve for our zeros. So let's see what this looks like. All right, so now we have state the number of possible real zeros and turning points of the function and determine the real zeros by factoring. We are going to put this in quadratic form like the previous slide showed. First, we'll look at our exponent. We have 4 possible zeros, real zeros. And we have 3 potential turning points. What we're going to do is we're going to do just like the last slide showed. I'm going to rewrite this where we have like x squared, which is the same as x to the fourth. We have 3 and we have x squared in parentheses. And I'm going to say now that let u, we're doing what we call a substitution. So we're going to let u equal x squared. We're going to change all of our x squareds into u. So we have u squared. We change the x squared out. We get 3u minus 4. This is quadratic form. We can now factor it easier. For some of you, it'll be easier to factor from this form. So we have u minus 4. What multiplies the negative 4 that adds to 3, and u plus 1. And again, we're trying to find zeros here. Once we've factored it, we're going to plug the x squared back in for u. So now we have 0 equals x squared minus 4. And we have x squared plus 1. So now we have x squared minus 4. We can factor it further. We get x minus 2, x plus 2. We have that difference of squares again. And we have x squared plus 1. And when you set these equal to 0, if you do the first one, you get these work. We get 2 and negative 2. These are my solutions. If we take x squared plus 1, we can't factor it because it's a plus in between. And if we set it equal to 0, we get this. Well, we can't take the square root of negative 1 when we solve for x in the real number system, so this doesn't work. So the only real zeros we have are these two, because the x squared plus 1 we cannot solve. Those are imaginary zeros, complex number system. So this one, we only have 2 real zeros out of the possible 4. All right, last one. We're going to factor out an x first, because everything has an x in it. We always want to get these things as simple as we can. So we have x to the fourth minus 6x squared minus 16. Again, we're going to put this in quadratic form. We're going to let u equal x squared. So now we're going to say, let me rewrite this again first though, as x squared squared minus 6 x squared in parentheses minus 16. Sometimes it's easier to visually see this happening. Now we change our x squareds into u's. This is a u squared minus 6u minus 16. We did a u substitution. Now we factor what's in the parentheses, and what multiplies the negative 16 that adds to negative 6? Well, it would be negative 8 and positive 2. All right, so now we're going to replace all of our u's with x squareds. So we have x. These are all zeros, by the way. So we have 0 equals x, x squared minus 8 and x squared plus 2. We try to solve each of these. They're not factorable, so we set them equal to 0. Well, x equals 0. X squared minus 8 equals 0. Add 8 to both sides, you get x squared equals 8. You take the square root of both sides, and you get x equals the square root of 8 plus or minus. And we do want to simplify this. The square root of 8 simplifies to plus or minus 2 square roots of 2. We can break square root of 8 into square root of 4 times the square root of 2. That's where I get the 2 square root of 2 from. The x squared plus 2, if we set it equal to 0, it's not going to work. You're going to get x squared equals negative 2. And we can't take the square root of negative 2 in the real number system. So our zeros are x equals 0 and plus or minus the square root of 2. 2 square roots of 2. We have 3 real zeros. When we started this problem, we had 5 possibles. I forgot to do that at the beginning. And we have 4 turning points that are possible. When we solve it, we find we have actually 3 real zeros. 2 of them are imaginary zeros. All right, let's keep moving on. Here we have repeated zeros of polynomial functions, and you've seen this before. So if we do a factoring, we get x minus c, x minus some number raised to a power. Then c is a factor and it has a multiplicity of whatever that exponent is. So when you get a binomial raised to a power as one of your factors, that number inside has a multiplicity. We call it the multiplicity of it. So if a 0c has odd multiplicity, then the graph crosses at that point. If it has even multiplicity, then the graph just touches the axes, the x-axis at that point. We say it's tangent to the axes because it does not actually cross at that point. Let's see what this looks like. So here it says, state the number of possible real zeros and turning points of the function. Determine all the real zeros by factoring. So the first thing we're going to look at is our exponent. Our n is 4. This means we have 4 possible real zeros. And then we take that number minus 1, and this is our possible turning points. We have 3 possible turning points. We can do that just by looking at this, by our leading coefficients power. So we know that we have 4 possible real zeros and 3 possible turning points. Now it says to find our real zeros by factoring. So we are going to factor this, set our factored form equal to 0, and see what our zeros are. Our leading coefficient in this case is a negative 1 with x to the 4th. All of the terms have x squared in it. To make it easier, I'm going to factor out a negative x squared. This becomes x squared inside the parentheses plus x minus 2. And we factor. Keep that negative x squared. We have x plus 2, x minus 1 is my factored form. We're going to set this equal to 0 because we're trying to find our zeros. So you show that. So if 0 equals negative x squared times x plus 2 in parentheses times x minus 1. And so my zeros are 0. 0 has a power of 2, so this is a multiplicity of 2. And we will state that. If you would look at a graph, since it's a multiplicity of 2, this would just touch the x-axis. It would just brush it. It has a tangent there. So it's barely going to touch the x-axis and bounce off of it. Then we also have negative 2 as an answer and 1. These have a power of 1. They will cross at these points. So it would cross the x-axis here. So when we get to graphing tomorrow, we'll use this to help us graph. And this is, it bounces off. This is how we do these. This is how I look at it as it bounces off. So when you do this, when you factor it, state your multiplicity. Tomorrow we're going to graph off of these so we understand what's happening with these multiplicities. All right, let's do another one. Here we have g of x equals 3x to the 5th minus 18x to the 4th plus 27x cubed. We are going to do the same thing. How many zeros? We have 5 possible because our highest exponent is 5. And we take 1 away from it to find our turning points. So we have 4 possible. And this is turning points. Then we factor it. Every term has a 3x cubed in it. So we can factor out a 3x cubed. leaves behind an x squared minus 6x plus 9. This is equal to 3x cubed. Then we have x minus 3. This is a perfect square trinomial, so it becomes a binomial squared. So we have x minus 3 all squared. We set this equal to 0, and our zeros are 0 with a multiplicity of 3. So again, when we graph this, this is going to be where it crosses, because it has an odd multiplicity, crosses x axes. You don't need to say that last part today, you just have to say the multiplicity. And we have an answer of 3, and this is a multiplicity of 2. And here it's going to bounce off. So we're going to keep this in mind for tomorrow when we graph these. This is what we'll be doing for part of our assignment today, looking at that leading term. Make sure everything's in standard form, of course, but look at that leading term. Look at the exponent. That's the number of possible zeros. Subtract 1 from it. That's the possible turning points. Factor it to find your zeros. And then it has a raised to a power, has a multiplicity of that power. Odd multiplicities, tomorrow when we graph, we'll be crossing the x-axis at the points. And if it has an even multiplicity, it bounces off the x-axis. Just touches it and bounces off. All right, coming to the last portion of today's notes. So here, if I give you the solutions in degree, we want to be able to write the polynomial. So it says, find a polynomial function of degree n with only the following real zeros. More than one answer is possible, because you can write these all sorts of different ways. So we have 0, and we have -4 as our two solutions. And we have a exponent that's going to be 5 that we have to get when we multiply everything together. So our multiplicities have to add up to 5, but we only have two solutions. So what we have to do is figure out how to make this work. There's different ways to do it. I'm going to use the easiest one. Since we have an answer of 0, if I just have, and I'm going to call this f, if I just take x and raise it to, let's say, the 3rd power, actually I'll make it even easier, I'll raise it to the 4th power, that means I have to have in parentheses x plus 4 raised to 1 power. This is going to give us 5. If we multiply this together, we would get x to the 5th plus 4x to the 4th. Our highest exponent is 5, matches, and we have two solutions. This would be my polynomial. This is one possibility. You could put the power of 4 on an x plus 4. You could change it to be the power of 2 and then power of 3, as long as the power is up to 5. Multiple ways to do this. You're going to have multiple different answers. The next one, we have 3 solutions, and we have a exponent of 5, a degree 5 polynomial. Same idea. I'll call this one g of x. And we just have to rate these as factors. Remember, we're going to use it opposite signs. So x minus 1 is a factor. X minus 2 is a factor. X minus 4 is a factor. Right now, I just have a degree of 3 if I multiply these together. So we need to make one of these a higher power, or more than one a higher power. So if I just said, all right, I'm going to make this a power of 2, and this one a power of 2. If I would multiply this all together, I would have an exponent of 5. I would have a degree 5 polynomial. This gets rather convoluted if you have to multiply it all together. I would take this as your solution, your answer for your polynomial. That is all for section 2.2, day 2. Today we looked at, just by looking at a function, we could find out how many turning points there are, how many zeros there are. We can find out multiplicity. Does it actually cross at a repeated factor, or does it just have a tangent there where it barely touches the x-axis? Thank you for watching, and have a nice day.